Melanofusion Pharmacology, Passage of Drugs Across the Plasma Membrane, Part 6, Vectorial Transport. How will a solute move across an epithelial cell? It has to cross two membranes. This surface is attached to the basement membrane. Therefore, this is the base. Opposite to the base will be the apex or apical surface. These are the lateral surfaces. The base and the lateral surfaces together form the basolateral surface. So, do you know what separates the apical and basolateral surfaces? Tight junctions. To be absorbed, a solute must move from the intestinal lumen across the apical membrane, traverse the cytoplasm, and finally cross the basolateral membrane to enter the interstitial space. Obviously, if another solute is to be secreted, movement must be in the opposite direction. This passage of the solute across the apical and basolateral membranes in one direction is termed vectorial transport. Let's see how this works with the example of glucose absorption in the small intestine. Glucose is a large polar molecule. So, simple diffusion is not an option for passage across the membrane. Membrane transporters are required. So here, to facilitate vectorial transport, membrane transporters must be located in such a way that the ones facilitating uptake must be on the apical surface and the ones mediating efflux should be on the basolateral surface. Let's consider a scenario after a high carbohydrate meal. Here, the glucose concentration in the intestinal lumen is relatively high. Clearly, a concentration gradient exists. Therefore, the transporter has to merely facilitate the diffusion of glucose. So, among the transporters we discussed in the previous videos, which one will it be? ABC or SLC? SLC. Here, the SLC transporter is GLUT2. With continued uptake, the glucose concentration within the cell increases. A concentration gradient for glucose is established between the cytoplasm and the interstitium. So here, if a transporter is available, glucose can move along its concentration gradient. This transport can be facilitated once again by GLUT2, but this time located on the basolateral membrane. Now, didn't we say that SLCs mostly mediate uptake? Yes, we did. But they also mediate efflux. GLUT2 is an example. This vectorial transport of glucose is dependent on apical GLUT2 and high glucose concentrations in the lumen. But here is a catch. The expression of GLUT2 on the apical membrane is a matter of debate. Also, when glucose concentration in the lumen is low, GLUT2 is not an effective transporter of glucose. So, how then is glucose absorbed regardless of its luminal concentrations? For this, concentration gradient of another solute is utilized and glucose is transported along with it. Here, the solute is sodium ion. The SLC that co-transports sodium and glucose is sodium glucose cotransporter 1 or SGLT1. Again, glucose concentration in the cell increases. This glucose can now be transported, as seen before, through the basolateral GLUT2 to eventually enter circulation. But if sodium continues to accumulate in the cell, the electrochemical gradient for sodium will eventually be abolished. Glucose uptake can come to a halt. To prevent this, the accumulating sodium ions must be removed. However, we know that sodium is an ion with a higher extracellular concentration. So, efflux must be against its electrochemical gradient. This requires energy. Do you remember the discussion of a pump that effluxes sodium against its concentration gradient? This pump, located on the basolateral membrane, is the sodium-potassium ATPase. It hydrolyzes one molecule of ATP to mediate the efflux of 3 sodium ions in exchange for 2 potassium ions. So now you can appreciate why different types of transporters and pumps are needed on the apical and basolateral surfaces of the cell membrane to facilitate vectorial transport of solutes. Please read this important note before you proceed. Here are some good to know facts. This is a summary of our discussion. In the next video, we will discuss the pharmacological relevance of membrane transporters.